Hi everybody, and thanks for joining the Right Talk. I'm Wolle, and today I'm going to talk about my favorite subject, which is real-time databases, and why most of them don't scale. But before I start with the actual content, let me briefly introduce myself. As I said, I'm Wolle, but you may also call me Wolfram Wingerath, and I'm currently a PhD student at the University of Hamburg, where I'm writing on real-time databases and related technologies. So I'm mostly concerned with the stuff I'm talking about in this talk, and also with stream processing technology, NoSQL databases in general. And I also dipped my toe into database benchmarking a while back. Also, I'm a software developer for the backend as a service startup Backend, where I'm basically engineering the real-time database component, which I'll also introduce in this talk later on. Louder? Could you turn me up, please? Thank you. I'm turned on now. So, okay, this is the outline of the talk today. I'll start with the first part because it makes sense, and it's going to be a motivation of push-based data access in general. So I'm going to contrast real-time queries against regular pull-based queries, and then we're going to go into the real-time database systems part, where we'll dissect the individual architectures of the most popular real-time databases. Then we'll discuss what problems we have uncovered, and finally we'll basically see how we at Backend developed scalable real-time queries that avoid the bottlenecks that current state-of-the-art is subject to. So let's talk about push-based data access. So databases, as you know them, are basically request-response style interaction systems. So a client on the left can ask a query, and then we'll get a response. And in this example, we have a client who's interested in circular shapes, and we have a database that stores different shapes, so squares, triangles, and circles. And while the client on the left periodically asks the same question, so can you give me some circular shapes? Some other clients, those are the guys at the bottom, keep reading and writing stuff. And the thing is that the client knows what he's interested in, namely circular shapes, but the database doesn't really keep him up to date. So he has to ask the same question again and again. And now you see that the client already knows there's a green shape, but when he asks the question again, you know, what's the current state? So what about these circular shapes? The client will receive the entire result again. So that's obviously inefficient because the database keeps sending the same information over and over, even though the client already knows that. And in between these polling intervals, the client basically has stale data because the client doesn't know what's going on the database side. What you actually want in many applications where you have some kind of notion that your data set is evolving, you basically want the database to push updates to you. So to illustrate the usefulness of a database that can do that, we implemented this showcase here a while back. So you can see that there's a room plan at the bottom. We have room A, B, C. And in room B, we deployed some sensors and tracked the motion of different people who were moving about. Those are the colored dots there. And when people were moving, then our web interface on the top right was just updating. And all it does is basically it shows all the people in room B sorted by their forename and shows their coordinates in the brackets behind their names. So the database query is the thing on the left, and the magic that happens, so that makes the database push the information, is only the keyword result stream, because that's our keyword for please give me the up-to-date result whenever something changes. And as you also see is that when another guy enters the room, then we don't only update the individual objects, but the query is changed in such a way that there's a new entry and it's sorted in the second position now. And when the guy leaves the room again, then the representation also changes in the sense that an item is removed. And that's pretty nice because the application developer, if he can just say, okay, this is my critical data set, so the query, and please give me the initial result and keep me posted when stuff changes, that's very powerful because the developer doesn't have to think about, okay, what's the appropriate polling interval and how can I, mock real-time behavior with my system which doesn't support that. So that's basically the reason why push-based data access is very cool in general. And now, since this particularly in the web and in the context of collaborative applications has been acknowledged as a problem, there are different systems that provide this functionality, so push-based data access. And these systems are basically called real-time databases. Meteor is, I think, one of the most popular systems and has been around for some years now. So initially introduced as Skybreak, it was rebranded as Meteor after roughly 1 year. And it's a JavaScript app and web development framework and uses MongoDB under the hood. And the cool thing about Meteor is that it basically provides the full MongoDB query expressiveness. So it's very powerful what you can do with Meteor, and it also keeps you up to date on your query results. And it's also open source, so it's licensed under the MIT license. And if you don't, feel like running your own infrastructure, you can also use Galaxy, which is the managed service they introduced like 2 years ago to cash in on the product. There are 2 different strategies that Meteor uses to provide you with push-based queries. And the first, so historically speaking, the first one is poll and diff. So poll and diff basically says, I'll explain. So you see the basic setup is you have the database, which is some MongoDB, and that's the silver thing in the middle there, and you have clients on the left and application servers on the right. And the idea is that the app server has some real-time query subscription, so it knows some queries that the clients want to keep get updates to. And whenever some client writes something, the app server checks whether this is relevant for some subscription and then notifies all clients that have the corresponding real-time query. So this is pretty straightforward, but if you have an app with many users and you want to scale, you might have several app servers. And now the problem can be that when the update arrives at the server on the right, then the server on the left doesn't really know about that. So because the write operation is applied to the database and the other server doesn't get a notification. So this problem basically is solved with poll and diff by periodically polling the same query and then diffing the result so that the client on the left would execute every real-time query that is currently subscribed every 10 seconds, then get the result and check whether this still is the same that it locally has maintained. And if not, it knows, okay, something happened, and that's the way that the left server would recognize the green item there was written by another server. This is basically a nice idea, but the problem is that it introduces huge staleness windows, because if you poll every 10 seconds, it means that you basically might have stale data for 10 seconds. And if you have something like a chat application, 10 seconds is quite a while. It's real time, as in not a magazine or something. You want low latency. And the other issue here is that it doesn't scale, because if every app server has to poll every real-time query every 10 seconds, or any other delay you choose, it means that even if you have an idle system where nothing is written, you always have this constant query load. So, for example, if you have 10,000 users, this means that even a system that doesn't do anything has 1,000 queries per second. And if you have an application with hundreds of thousands of users, this will blow up in your face. So that's basically not a secret. So the Meteor guys came up with another approach, which they call oblog tailing. And it's basically called like that because the idea is to tail the oblog. And now you might ask yourself, what is an oblog and how do I tail it? And so that's what I'm going to explain now. The idea is that Meteor uses MongoDB, and MongoDB is a sharded database. And you see here 3 database shards. So those are called primaries in MongoDB lingo. Sorry. Yeah, and every primary has several servers that copy everything they do. So those are called the secondaries. And whenever something is written, the client contacts the primary, sends the data is then applied at the primary and forwarded to the secondaries. So the idea, remember that, of sharding the database in the first place is that you assume the write throughput will be too heavy for a single server to handle. So that's why we have 3 primaries, and this write operation only goes to primary C, and the other primary A and B don't see the write operation. Now every secondary only follows one single primary, because remember, write throughput might be tough. And the idea here of the oblog tailing approach is that every app server subscribes to every oblog, so pretends to be a secondary and thus receives all write operations. So in this scenario with oblog tailing enabled, the write operation that is received by the write server would basically be broadcasted to all servers that are listening through the op log, and then the left server would immediately get notified. So this solves this polling problem because the left server doesn't have to poll for the query. It may, however, be necessary to poll the database for some updates on the received write operation because the op log might contain only partial information and then it's incomplete. So additional information might be retrieved from the database, but eventually with rather low latency, the app server on the left can notify all clients with regards to the relevant data. So now I just mentioned that the information provided by the op log may be incomplete. Let me give an example. Imagine your real-time query is something like, give me all top high-score players for some game. For example, Baccarat. So we say if, we have the top 3 here, and Joy, Tim, and Lee have 190 and 80 points as a high score respectively. If through the op log an operation arrives that says, hey, Bobby has a new high score, it's 500, then yeah, well, that's nice. But we don't know whether Bobby is a Baccarat player or not. So in order to determine whether it's actually relevant, we have to ask the database, what game does Bobby actually play? And if he's a Baccarat player, then he'll take the first place because 500 is pretty high up there. If he plays Space Invaders, then he's a loser and we don't care. So that's basically the question that the database would have to ask here. And that's not even the problem because, making point lookups at sometimes isn't too hard. The really hard thing is that every app server, as I mentioned earlier, has to subscribe to all op logs. So you shard the database on MongoDB level because you assume MongoDB can't keep up with the write workload. But then again, you say, okay, but every app server can do everything all the combined MongoDB primaries can do, and that's just not working. And that's an actual problem, so that op-log tailing doesn't scale with the right throughput. Okay, so that's basically all about Meteor real-time queries, and let's look at the next system, which is here RethinkDB. And RethinkDB is similar to MongoDB with respect to query expressiveness and data model, and therefore is sometimes referred to as MongoDB done right. Because it's very similar, but it also has some cool features. For example, real-time queries, that's basically why it's on this list here. And also better support for non-streaming joins. And it's strongly consistent, what is something cool when you come from MongoDB. It has also some Galaxy-similar web development framework on top, which is called Horizon. And you can also check that out as open source. So that's pretty cool. RethinkDB is available under the Apache 2 license, which is important because the company backing RethinkDB has shut down, so it can be developed by the community nowadays. And here's the overview over RethinkDB change feeds, which is their term for real-time queries. The basic idea is similar to op-log tailing because you have a sharded database, which is not Mongo, but still is sharded, and every database shard basically streams the updates to the RethinkDB proxies, and the proxies are the processes that do all the client interaction, basically. And the problem is the same as with op-log tailing, because since every app server, so every RethinkDB proxy, has to subscribe to the entire overall system write throughput, the overall system write throughput is also bottlenecked by single node capacity because it has to go through the RethinkDB proxy. That's it for RethinkDB. Now let's talk about the next system, which is Parse. Parse is pretty popular, or was pretty popular, and around 2015 they had like 500,000 apps running on their infrastructure. They are a backend as a service for mobile app development and are also running on MongoDB. At one point they had the world's largest deployment, and they were pretty nice, especially because they had great documentation and many features that made it just so easy to build applications that were running fast on their infrastructure, so that you get stuff up and running to, whatever prototype or so. They are open sourced now, and their own managed service has been discontinued because they had first been bought by Facebook, which was cool, and then they were shut down, which was less cool. And this announcement was in 2016, and at the beginning of 2017, it went into effect. But it's still relevant because they had so many customers that Azure and other providers jumped onto the bandwagon and provided, service for the customers, so that backend Parse apps are actually running on other infrastructure nowadays. Well, however, Parse also introduced real-time queries in March, I think, this year. And the general architecture looks something like this. You have the Parse app server layer on the left. So there's a horizontally scalable layer of servers who do the client interaction for OLTP and queries and stuff. And on the right, you have the clients for real-time queries. And as you can see, the clients for real-time queries don't connect to the actual app servers, but to live query servers. And those do the maintenance for the real-time queries. And this is pretty similar to RethinkDB and oblong tailing, actually, because the write operations that arrive at the Parse servers on the left are then written to a Redis-based message queue and broadcasted to all live query servers. And the word broadcast is again nasty here, because it means that every live query server has to process all write updates, and that's again the bottleneck here. So the thing is basically similar to oblong tailing and has the same problem. Yeah, the last system on the list here that we cover in more detail is Firebase, and it stands out in particular because it's absolutely not open sourced, and it's actually not even disclosed what their technology stack looks like. So it's hard to evaluate how scalable they are. But they are pretty interesting nonetheless, because even though their concrete technology is not disclosed, it's pretty clear what trade-offs they are going for here. And you can see that because all other systems discussed so far are basically document databases that have connections of JSON documents as application data model. And Firebase here is basically one huge JSON file. That is, if you have a Firebase application, you don't have a set of JSON documents, you only have one big JSON document. And all queries that you can do are basically navigating through this tree of lists and objects. Yeah, that also means that your queries are, your data model is not as sophisticated, and your queries are simpler, but also everything is fully real-time, and that's basically what Firebase is known for. It's hosted completely on Google infrastructure and is integrated well with Google services. So that's very great about Firebase, I think. But as I say, the general idea is, even though real-time query is often heard in the context of Firebase, rather real-time state synchronization. So you can subscribe to particular subtrees of your JSON data model, and when something happens in that particular subtree, then you receive some notification. Yeah, it's basically, theoretically you can do complex structures with that, but the official recommendation is to clutter everything flat for efficiency reasons. And I think that's basically why you can say that Firebase doesn't really scale, because, of course, if you only do like point access, it's pretty performant. But the thing is, if you have complex and sophisticated use cases, then it's hard to solve the problem actually with the database capabilities, and you end up putting much into, for example, denormalized attributes or processing in the client, and that's not what you want from your database. So let me give an example. If you have a chat application, you would have something like messages and you have something like users. And if you model that as a tree, you basically have to decide, okay, should I use the message and put the user under there, or should I use, a user and then the message is a child of the user, or should I just reference everything wildly in the tree? Or, that's just hard to do in Firebase. And it's particularly hard because you can only order by a single attribute. And if you want to filter stuff, you also can only filter by one single attribute. And in particular, you can't do anything like a logical and or, and that just makes it hard to formulate queries in Firebase. So there are also other systems that have real-timey features, and I want to briefly gloss over them. So I think the more complex capabilities are found in Realm, GraphQL, and RapidIO. So Realm is, I'd say, some kind of replacement for SQLite. So the use case is pretty much geared towards small data sets. So the real-time processing is sophisticated, but it's happening in the client, and that's basically, that makes it not particularly scalable if you're talking about big data applications or something like that. GraphQL and RapidIO look very promising from their documentation, but I'm actually not aware of any big use cases, so we'll have to see whether and what comes from them in the future. CouchDB and OrientDB have some kind of filtering capability on the change stream, so you can subscribe to kind of real-time queries on the stream of change operations that happen. Yeah, and MongoDB has announced to introduce some real-time API, but I didn't hear from them in a while, so I don't think that they have something right now, but it's, it's coming. Okay, so now we've seen basically the state of the art in real-time queries, and I'd like to talk about what we've seen here and compare the systems. So let's talk about the big picture first. So we have seen real-time databases, and their underlying notion of data is basically an evolving collection. So evolving collections are, in contrast to static collections that normal databases have or want you to think about. It's like an Oracle database encapsulate a consistent snapshot of your application data at one point in time. And you can ask a query, and then you get an answer regarding this particular point in time. But if your application requires you to keep track of changes because you are collaborating with other users or something like that, then Oracle makes it hard for you. And real-time databases try to acknowledge that you want to think about evolving things, and therefore they have the same semantics with regards to query. So if you ask the question, you think about the database collection, but you also receive the changes. And that's basically the contrast to normal databases. On the other side, so that was, on the left is the pull-based data access. And on the right, there are systems that are more oriented towards push-based access, because they have also been around for years or decades even. But they are mostly centered around the concept of a data stream. So if you ask a query on a data stream management system, you don't ask some database and have a collection in mind, but it's some, something that is explicitly ephemeral, and that you see some change operations in a stream, and once you've processed them, they are gone. So the semantics are quite different. And that's basically unique to real-time databases, that they take the middle ground between static collections and evolving data streams here. And the systems we've seen here have very many properties, and we try to organize them in this matrix here. So I think the most important properties actually are the first two rows. They are the scalability rows, and they are, in my opinion, most important, because if your system is not scalable, you actually can't use it, because if your customer base is growing, then you're pretty much dead, because your system doesn't run anymore, and that must not happen. And as you can see, Meteor is the only system that can scale with write throughput, because it supports two different modes. So the poll and diff approach is scalable with write throughput, but since it keeps polling the database again and again, it's not scalable with the number of queries. And all other systems, apart from Firebase, that's what I'm going to talk about right now, they don't scale with the write throughput. So that's also another problem. And with Firebase, it's hard to tell whether it scales and to what degree, because we don't know how it works internally, and we only know the quota limits and restrictions. And for example, there's a hard limit documented in Firebase that says you can only have 1,000 client connections, and if you want to go beyond that, you should spin up another instance. So there seems to be some limit, and we can't really say whether that's fixed or whether they could actually theoretically ramp it up. But it's Google, so they won't, I guess. With regards to querying expressiveness, we see that Meteor is heads up and basically supports sorted queries with limit and offset, because it supports complete MongoDB queries, and it also supports composite queries with and or. And RethinkDB basically is similar, but it doesn't support offset for some reason, so only sorted queries with limit. And Parse doesn't support querying at all. It does support querying, sorry. It doesn't support sorting. And Firebase does support sorting, but it's very limited, because you can only sort on single attributes. And you also don't have composite queries there. So, and the question that we asked ourselves, and I specifically in my PhD thesis, is why exactly do these systems either not scale or do not provide expressiveness, like, for example, MongoDB? And I think there's no good reason, and that's why we at Backend build a system that is scalable and also as expressive as MongoDB. And that's what I want to talk about for the remainder of this talk. So how exactly do we achieve this scalability, and how do we avoid the bottlenecks that the other systems are subject to? Yeah, so at the core of backend real-time queries is InvaliDB, and that's the system I'm developing in my PhD thesis. And it's called InvaliDB because our initial use case was to invalidate database queries with it. And I want you to understand that, so I'm going to talk a little bit about what exactly backend does as a company so that you understand what exactly I mean with invalidating queries. So backend as a company is concerned with slow websites in the sense that we want to annihilate them and make them fast. And the problem that most websites that are slow are subject to is that you have a client, and the client fires a request. Then the database does some processing and sends a response. And this just takes a while because there's some processing overhead and there's latency between client and server. And now it would be very cool if you could alternatively, and that's what backend websites do, not ask the database, but instead ask a nearby cache. So you have low latency, and also you have less processing overhead at the backend because the request doesn't even go to the backend, but it's immediately basically answered by the cache. And the difficulty here is that the backend has to keep track of all the caches. And whenever a cache becomes stale, the backend has to say, okay, cache, please remove this data item and don't serve it anymore, so that the outdated data items actually are served by the backend. So, and this is rather easy for, you know, like if you cache data objects by their ID, because you can monitor and keep track which data items you update, and when you update an item, you purge it from the caches. But for queries, the situation is more involved, and that's where InvaliDB comes in. So imagine you have a web shop and your users want to look at current products, like give me the most popular items that match my filter query and that are in stock. And in order to make sure that when this is served from a cache, the cache is invalidated once another, you know, like imagine one of those items is bought and goes out of stock, then you can serve this from a cache. And to determine whether or not you have to invalidate a cache, you must look at every database operation that hits the database and check whether an item is added, changed, or removed. And that's pretty complex, and it's basically like maintaining a real-time query, because you have to check whether any write operation affects the query. And we basically don't do that in the application server because it doesn't work that way, as many systems have demonstrated. Instead, we have a specific system here in InvaliDB, which does the real-time query matching. And whenever something is written, the application server just hands this write operation down to InvaliDB, and InvaliDB checks whether some query is affected. And if so, it hands the information back to the app server, which then purges the caches or delivers the update to clients so that they can maintain their local representation of a query result. So yeah, let's go into this a bit deeper. So you see there's a client on the top right, and the client is subscribed to some real-time query. And on the left, you see data coming into the system. And there's this big block, which is the backend app server, and there's a database also somewhere. And in the bottom, there's this dashed box where InvaliDB is. And whenever data is written, the app server applies it to the database and sends it down to InvaliDB, and InvaliDB checks, you know, whether this write operation has any effect on the database query. And the first two here don't have any effect. However, when the third item here is written, then InvaliDB checks whether this has an effect. And actually it does, because the yellow dot here should be sorted in the middle. So InvaliDB updates its internal representation of the query and sends this change delta, so incremental information that the client can use to update the client representation, to the app server. And the app server then gives it to the client. And now you see that the client has an updated result, so it's fresh data at the client, but the client didn't need to ask the entire query again. It just receives the data proactively. And the app server also doesn't really have to do anything. It just has to listen to changes and then pass them on. So that's what InvaliDB does, and that's the system I'm developing in my PhD thesis. And we've also put it into production at backend, so we can say it actually works at scale. Processing is in 4 stages in InvaliDB. The first stage is actually the critical one because that's the filtering stage. And this stage sees all write operations happening in the entire system. So it needs to be vastly scalable, and it also sees all queries. So we have very much to do in this stage. And the next stage, it basically decides whether a matching condition is fulfilled when it sees a write, or whether maybe some item that matched before is not matching now, and then you have to generate like, oh, you just lost an item or something like that. The next stage keeps track of ordering. So for example, it recognizes whether an item changed the position in the result set. And then we have other stages to do stuff like aggregation or so on. And as I said, the critical part here is basically the filtering stage. So that's where all other systems fail because they are not scalable enough. And we try to, we are more scalable than other systems because we scale with the number of queries and also with the write operations. So at the right, you see there's InvaliDB, and in the example, we have 9 matching nodes. So those are the little gear wheels there. Each gear wheel is a matching node, so a server. And we have query partitions and object partitions. And the idea is that whenever we register a query, then we determine the query partition this query belongs to. And every server that is in this partition receives the query. So here we have 3 servers that each maintain this query. And whenever something is written, we hash the ID of the written object, and then give every server in the corresponding object partition this write operation. So that also 3 servers see this write operation here. And what you see is that every query is matched against every write operation, but also every individual server only sees 1/3 of the write operations and also 1/3 of the queries. So if we need more users, we can also add more query partitions, and we can also add more object partitions, and then ramp up write throughput that is sustainable. So that basically means we can scale in both directions, and therefore don't have any bottlenecks here. We implemented that on top of Apache Storm, and MongoDB is our query language that we support by default, but it's pluggable, so we might implement something like Postgres later on. And here are some performance numbers. On the left, you see sustainable matching throughput with increased number of matching nodes. So on the left, you see the single node capacity just below 5 million match operations per second. And if you add like 16-fold nodes, you also get 16-folds in sustainable throughput. So it scales absolutely linear. And on the right, you see that the latency characteristics are stable. So the single node cluster is the blue one, I guess, yeah. And the 16-node cluster is the orange one. And if you put them above one another, they basically look alike. So you don't really have deteriorating latency, even though you can increase throughput as you wish. And if you want to read more details on that, we have a VLDB paper on the issue. And there's also some YouTube video of our VLDB presentation. Okay, and how can you use that actually as a developer? So backend has a query API that works with query objects that are built with this builder pattern here. So in the example, we see that we want to have a query on the database on the tweet collection, and we only want tweets that match our regex pattern, sorted in descending order by their creation date, and we want to skip the first 20 items and only want to have 10 items after that. So if you want to execute the query, we can either call the result list method and provide some callback that renders our result, or we could use the result stream method, which basically works identically from a developer point of view, but will call the callback here that renders the result once upfront when you receive the result the first time, and every time there is a change. So you actually don't have to think about events or anything. You only think about the result of your query, and whenever something changes, the result stream thing here will invoke the callback. And we implemented a showcase that is called Twoogle, and it is basically a query on a collection that we render into the web, into a website, and we keep inserting tweets from the Twitter API into our collection and only execute one real-time query. And as you can see, it's working pretty nicely. So on the left, you see a browser window where we type something like Java in order to filter for Java-related tweets, and on the right, you see that stuff keeps happening. And whenever something happens on the left, it's because the Java keyword there is contained in the tweet, and on the right we see all other tweets as well. And what's also pretty neat is that we support limit and offset queries, so we can implement pagination pretty easily just by using offset and limit. And that's quite a hassle if you have a system like RethinkDB, where you only have limit and not offset, or Parse, where you don't have sorting at all. You can try this out, by the way, on google.info. Yeah, that's basically the meat and bones of my talk. So to wrap things up, push-based data access is pretty cool and is natural for many applications, but if your underlying data store only supports pull-based data access, sucks to be you. Real-time databases, yeah, promise salvation because they are natively push-based, and the thing is they usually don't scale, so you can use them. But other than that, they are pretty nice. And if you use backend real-time queries, you can scale, and you also have the basically the same expressiveness as with MongoDB, which is pretty powerful already. Yeah, so we have related scientific publications on both InvaliDB and our backend architecture and on related technology. So please check them out if you're interested. And we have a company blog. And in particular, we have a blog post on this exact talk. So you can read everything up there. Visit blog.backend.com if you're interested. OK, Backend is also hiring. So if you're talented, I can connect you with the right people. Give me an email. Yeah, and I think that concludes my talk. We have 3 other talks on real-time and backend in general tomorrow. So at 10 o'clock, you'll see a real-time application being developed live. And that's pretty nice. And at 2 and 5, you'll see details on fast web applications and the backend technology stack. So yeah, thanks for your attention. I think I'm ready for questions now. So I'd have more questions and I'd have listened to this talk. Yeah.
So basically just a short question with probably a long answer, but where's the catch? Like, what's wrong with your database?
Yeah, the thing is, you know, I'm currently writing my PhD thesis, so I can't answer that. No, I think you'll have to try it out yourself. I mean, what am I going to say? I mean, there are problems with MongoDB, and everybody uses it because it's cool. I think it's a new technology. You know, this entire real-time thing is hard to grasp. So I've been working on the real-time thing alone for like, I think 4 years now, and I've done nothing else. And we have 12 developers in the team, and I think I have burned like 2 man-years in fixing bugs alone with the help of my colleagues. So I think we have just, you know, a very stable system right now. And if you look at Meteor, those systems have been around for 6 years, and they are still very buggy. So I think just using a better architecture is a big heads up. So I'm glad if you tell me what's wrong with the system if you try it out.
Thank you for the great talk. I would like to ask if you could repeat some or say some more words about the partitioning slide you showed us. I didn't get it.
I'd like to do that. This one? The basic problem that the other systems have is that they say, okay, we have a query, so I need to, you know, retrieve the query from the database, and then I look at every write operation and say you have something like give me all products that match the word TV screen, and you know, sort them by price. So you have to monitor all write operations. Is there a new TV screen, or is one of the existing ones changed in price or something like that. And the problem that all other systems have is that this task of monitoring the query is given to one particular server. And that's the reason why it has to see all the write operations, and that's the reason why it breaks. And what we do here is we basically split up the query maintenance, because we have one, this highly scalable layer that only checks the matching condition. So give me all matching items with TV screen in them. And we partition them by ID, so we can give any node here an ID range, and then it monitors only this range and generates something like, hey, we have a new match, or hey, this was a match and it's not matching now. So that means you highly reduce the number of events that are fired if then the next stage is the one that monitors something like sorting. So if you have something like, okay, this one here was an LCD screen and now it's not anymore, then you give that to the next layer. There we have one server that monitors ordering, but that's not really hard to do, because you don't see write operations on the entire cluster. You only see the TV screen write operations. And you may even do optimizations like keeping some indexes locally and so on. That's a bit complicated here, but the idea is basically that by having these, now my handy went off, whatever. The idea basically is that by structuring this maintenance task into the highly scalable filtering stage and other stages to do stuff like sorting, makes it scalable. So we don't cram everything up into one process, basically. You're welcome. Yeah, there's another question.
Hello, I have two questions. First one, so how much hardware do you need for this kind of thing? Because it looks you need probably a big cluster to do modern big application stuff. The other question would be, how do you guarantee consistency and things, especially like primary key updates and such things? Because when you have partitioning, you will get some problems, probably.
Okay, so the second question first, because I think it's, it doesn't care. Let's say the first question first. So the hardware question is basically you don't need that much hardware to make it run. So we have a development server where we have a local Storm cluster and everything running locally, and you can work with that. So in order to get performance, you want to use something like some server, but it's rather low overhead because well, it's all natively running in Java, and Storm is pretty efficient. And yeah, I think we had like EC2 instances like C3 large in our benchmarks, and they had like, I don't know, 2 virtual cores and 2 gig of RAM or something like that. And you could get something like 1,000 concurrent queries and 3,000 or 4,000 write operations per second from one node. So I mean, I don't know whether that helps. And the consistency question is first, we don't allow changes of the primary key because they are basically generated at the client so that you can insert new items without coordination. That's just a UUID, and that's final, and we don't allow you to alter that. And consistency-wise, we have, I say, something like eventual consistency. So because we have various kinds of race conditions everywhere here, and we don't really know whether the write operations are received in the same order in our system as they are by the database. So what our system does is it applies the stuff and says what MongoDB would say, but if MongoDB receives it in another order, then you could have things that go astray for a while because you see an insert before MongoDB or the other way around. But when we see all operations that MongoDB does, the order doesn't really make a difference because the end result will be the same. So you would have like, I don't know, maybe differences in the order of milliseconds.
Okay, thank you. Time is over.
Yeah, thanks for the nice experience.